But before we go to the physics part, let's do as always. So any thoughts of which one of these two depicts the right interface between a quantum spin Hall insulator and a quantum anomalous Hall insulator? Right. So yeah, so we have on the right. So anybody thinks that it's the one on the left? Right. Yeah. So absolutely, the right answer is the one on the right. So the basic idea is that the quantum spin Hall insulator would have two helical edge states here if the Chern insulator was not here, but the Chern insulator kind of destroys one of them, and you only have one left. So in this picture, you can think that the one that gets destroyed is the blue one. All right, great. So now let us move on to Wally-Chern insulators, namely systems that do not break time-reversal symmetry, that they don't have spin-orbit coupling, so that you cannot have these spin helical edge states, and yet they still have emergent topological states driven by Berry curvature. Let me emphasize that all this idea of Wally-Hall insulators is especially important in graphene and in general in systems that have Wallis in their electronic structure. So for having Chern insulators or for having quantum spin Hall insulators, you don't need any specific features on your electronic structure. You can have any kind of complex electronic structure with, let's say, many bands, not well-defined pockets. And if you are in the right regime, you may get a Chern insulator or quantum spin Hall insulator. But to get Wally insulators, you need to have a very well-defined electronic structure with something that you can call Wally. And in particular, that is, of course, something that happens in graphene and that it also happens in some other TMDs. But for now on, let's just focus on graphene multilayers, in aligned graphene multilayers. And in particular, let's think about the simplest graphene multilayer, which is the case of bilayer graphene. And in the case of bilayer graphene, we are going to take the Bernal stacking, which is the AB stacking, which essentially means that let's say 1 every 2 atoms is on top of the other atom of the other layer. And in these twisted graphene bilayers, we can actually apply a bias between the layers, which essentially means that we take a voltage between the bottom and the top layers, which is, of course, something that you can control electrically. And as we briefly discussed in the previous session, once you take this bilayer graphene and you apply a voltage, you essentially open a gap in your electronic structure. And this gap in the electronic structure is proportional to the voltage that you apply, and it saturates to a certain value when the bias between the layers is on the order of the interlayer coupling. But the important point here is that in the very same way as in monolayer graphene, when we added a mass, here, when you open a gap, you generate Berry curvature. So the color here of the bands is the Berry curvature of the bands, or the Berry curvature that you obtain when you apply a bias. And what's actually important for us is that the sign of the Berry curvature actually depends on what is the sign of your bias. If you apply a positive bias, then your Berry curvature is going to be blue. If you apply a negative bias, then your Berry curvature is going to be red. What this actually means is that the Chern number in this valley is going to depend on the bias. If you apply positive bias, you get Chern number 1 for bilayer graphene. If you apply negative bias, you get Chern number -1 for bilayer graphene. And of course, this has many important consequences. So the first one is that if you think about a bilayer graphene in which you apply positive bias in one part of the sample and negative bias on the other part of the sample, you are essentially going to generate a Chern number positive in one part of the sample and a Chern number negative in the other part of the sample for this valley, of course. And since you have opposite Chern numbers for this valley, you are going to create interface states. Now, the important thing to remember is that, of course, when you are applying a electric field, you are not breaking the reversal symmetry. So your total Chern number must be 0. The total Chern number of your system needs to be 0. But what doesn't have to be 0 is the difference of the Chern number between valley k and valley k prime, specifically because the bias breaks inversion symmetry, and when we break inversion symmetry, the valley Chern number can be non-zero, and that is exactly what happens in biased bilayer graphene. So The basic idea is that as you go from negative bias in bilayer graphene to positive bias, you essentially switch the colors of your Berry curvature. So as I mentioned before, negative bias gives rise to, for example, blue, red, red, blue in opposite valleys, and positive bias gives rise to the exact opposite one. So if you now consider that momentum, that valley is a good quantum number, which is this degree of freedom that we get in graphene multilayers, then you can think about the Chern numbers of one valley and the Chern numbers of the other valley. And in this way, one of the valleys realizes one Chern insulator, and the other valley realizes the opposite Chern insulator. And let me note that this is exactly the very same idea that we were describing for quantum spin Hall insulators. In the case of quantum spin Hall insulators, we were thinking that spin up has one Chern number, spin down has the opposite Chern number. Here, valley K has one Chern number, valley K prime has the opposite Chern number. And if we assume that valley is a good quantum number, then we have the very same phenomenology as with quantum spin Hall insulators. So the basic idea is that if you now think about a finite system, a finite bilayer graphene in which you apply a bias, what you get is that, of course, in the bulk of your system, you develop a gap, which is the very same gap that you had when, in the two-dimensional electronic structure. But now, due to this finite Berry curvature, due to this Chern number in each valley, you essentially get states that propagate in one direction and states that propagate in the opposite direction in the different valleys, in the different edges. And what it's actually important to note is that the actual valley quantum number of these states is different. So for example, if you focus on a single edge, which is, for example, let's say this red band here, what you actually see is that within that edge, one of the states belongs to one valley and the other state belongs to the other valley. And let me emphasize that these colors here are not just colors that I put by hand to help you see this. These are actually the expectation value of the valley number in a tie-binding model. So one can define a valley operator in a real space basis, and if you compute the expectation value of this valley operator, you essentially see that within this edge, one of the states has perfect quantization in one valley, the other state has perfect quantization in the opposite valley. So as long as the perturbations that you include in your bilayer do not break valley symmetry, then these two counter-propagating states are not going to gap each other. And which kind of perturbations do not break valley symmetry? So in general, any smooth perturbation in graphene is not going to break valley symmetry. So any smooth strain that you may have doesn't break the universal symmetry. It doesn't matter if it is uniform or non-uniform, as long as it is smooth. Weak disorder also doesn't break valley symmetry. And of course, let's say in general, let's say magnetization or spin orbit coupling also do not break valley symmetry. Of course, there are some perturbations that do break valley symmetry. And in general, the perturbations that break valley symmetry are perturbations that are associated to a very, very large scattering in momentum space. And what this actually means is to a very strongly localized impurity in real space. So for example, vacancies in graphene create huge intervalley scattering. So if your samples have many vacancies, that is going to create a lot of intervalley scattering and it may destroy these states. And there are also another type of perturbations that create intervalley scattering, which are perturbations with a periodicity of square root of 3 square root of 3. And maybe you can think about them in terms of periodicity 3 times 3. And this type of perturbations is what is called Kekulé distortion, which is a distortion in which you take 6 atoms in graphene and pull them together, and you do this every 6 atoms. So these distortions actually appear sometimes in graphene systems. And they appear, for example, when you put graphene on top of certain metals, like copper. So the copper drives a Kekulé distortion in graphene, and they can even appear because of interactions. So just electronic interactions can drive these Kekulé distortions. And in particular, in some twisted graphene multilayers, one has this interaction-driven correlated state that creates inter-valley scattering, that it's known as valley coherent state or a Kekule state. So it's a distortion in which valley is no longer a good quantum degree of freedom, and that breaking comes directly from interactions. So the way in which that can be understood is in the very same way as we understand magnetism. So in-plane magnetism is a spontaneous mixture of the up and down components, right? So any Kekule distortion driven by electronic interactions is also a spontaneous mixture driven by interactions of the up and down components of your valley degree of freedom. All right, good. So as long as we don't have intervalley mixing, we have topological states. But let me emphasize that this is something that not only applies to bilayer graphene and twisted graphene bilayers, but this also applies to generic twisted graphene multilayers. So now for concreteness, let me just show you ABC trilayer graphene. So this is rhombohedral graphene, so it's just 3 layers of graphene, one on top of another. So in the absence of an electric field, you essentially had this dispersion that was actually relatively flat and gives rise to a p to the third power dispersion at low energies. But now when you apply a bias, you open up a gap. And this gap, again, has a finite Berry curvature. And this gap, again, has a Berry curvature that changes sign once you change sign of the bias. So if you are with negative bias, for this valley, you get negative Berry curvature. And if you change the bias, you get positive Berry curvature. So this phenomenology that you observe in trilayers is the same as the one in bilayer. And if you go to a bigger number of layers, you still see this very same phenomenology. Eventually, once you have too many layers, you may have graphite, and this doesn't work anymore. But both for bilayer and trilayer, you can generate these valley-dependent Berry curvatures. And of course, that also has a consequence in terms of edge states for a trilayer graphene. So what I'm showing you here is the electronic structure of an ABC trilayer with an electric field. And you see that in this system, you again have these gapless states. And that, of course, if you compute the valley degree of freedom, you will see that they belong to different valleys within the same edge. All right, great. So now in the last 5-10 minutes, let me tell you a little bit about topological phase transitions, and in particular, how we go from a trivial insulator to a topological insulator, and in particular, what happens to the bulk and to the edge as we go from a topological system to a trivial system, or as we go between two different topological states. So, of course, at the beginning of today's session, I told you that for topological insulators, we cannot transform a topological insulator to a trivial insulator without closing the band gap. But if you are willing to close the band gap, then of course you can. So you can always transform one system to another if you are willing to do anything to your Hamiltonian. So let us start with a case of a Chern insulator. So we are going to take first a system with Chern number 0 and another system with Chern number 1. And we are going to see what happens if we try to, let's say, smoothly transform the system with Chern number 1 onto a system with Chern number 0. So here's the example that I'm showing you. So here on the top, you can see a certain parameter that essentially controls going from a Chern insulator to a trivial insulator. So that is the parameter M. And on top, you see what is the Chern number of your system. So in this case, you have a topological gap. And you can see that it's topological just from the Berry curvature. So you have the very same sign of the Berry curvature in both valleys. And therefore, once you integrate the Berry curvature, you are going to get an integer number in reciprocal space, that is the Chern number. Whereas in the trivial case, you have, let's say, both positive and negative Berry curvatures. And when you integrate it in reciprocal space, you're going to get 0 because this is a trivial insulator. So as you ramp up this parameter that interpolates by a brute force between a Chern insulator and a trivial insulator, what you actually see is two things. The first one is that there's a gap closing, of course, because by definition, we cannot transform one onto the other without closing the gap. So this gap closing is, of course, something that we knew it was going to be here. But what it's actually also interesting is that we also see a transfer of Berry curvature between the conduction and valence band. And of course, this is something that must happen, because if you want to go from Chern number 1 to Chern number 0, you need to put your Berry curvature somewhere else, and this somewhere else is the conduction band. So in general, every time that you have a topological transition, you are going to have a band touching, and this band touching is going to give rise to a transfer of Berry curvature from the valence band and the conduction band. What this actually means is that if you are, let's say, in a situation in which the gap is very small, you know that those states that are very close to this gap are going to have a lot of Berry curvature because are going to be the ones responsible of transferring Berry curvature from the conduction band to the valence band. All right, great. So this was in the bulk. So let us now see what happens at the edge. So here, what I'm showing you is the electronic structure of a ribbon with those very same parameters. So before was the bulk spectra, now was just the ribbon spectra with the same Hamiltonian. And you see that when you are in the topological phase, you have your chiral states. So red is one edge, blue is the opposite edge. So you have one state per edge. And now, as you increase this parameter, you start closing the bulk gap. So you see that these two bands touch. And when these two bands touch and they detach as you ramp up the parameter, you see that you no longer have edge states. So once you wrap up this parameter that interpolates between a topological insulator and a trivial insulator, you get, of course, a transfer of Berry curvature in the bulk that in the edge, it becomes just a transfer of crossings, let's say. So you go from a situation in which you have, let's say, one state that connects the conduction to the valence band to no states connecting the conduction to the valence band. So these two phenomena are actually a reflection of the very same physics. One is in the bulk, the other one is in the edge, but it's essentially the same idea. And of course, you can do the very same with a topological insulator, in particular with a quantum spin Hall insulator. So a system that doesn't break time reversal symmetry and that has helical edge states. So here in the system, we cannot, let's say, draw anymore the Berry curvature because the total Chern number is 0 all the time. But we can still see that there's going to be a gap closing. So you go from a situation in which you have a, let's say, finite gap and your topological invariant is non-trivial to a situation in which you have a trivial gap and your topological invariant is trivial. So here, topological invariant -1 means non-trivial and +1 means trivial. And of course, you see this on the bulk, but what's more important is what you see at the edge. So when you were in the situation in which your system was a topological insulator, you see a pair of helical states. So for example, you can focus on the red states that are both states that belong to the same edge and are going to be time reversal partners. So what you observe is that as you ramp up this value, you close the bulk gap and you have a transfer of Kramer's crossings in between the gaps. So you go from 1 Kramer's crossing in the gap per edge to 0 Kramer's crossings in between the edges. And of course, this very same phenomenology is something that you also see in any topological system. And let me now mention that, of course, for Chern insulators, we usually cannot interpolate between a trivial insulator and a Chern insulator, or a trivial insulator and a quantum spin Hall insulator, at least in the lab. So in the lab, 1T prime tungsten telluride is a topological insulator, and that's all. It's a quantum spin Hall insulator, and that's all. And you cannot interpolate that material with another material that it's a trivial insulator. But with topological superconductors, you can interpolate between a topological superconductor and a trivial superconductor, just because, as we saw in the second session, topological superconductors depend on the chemical potential that your system has. So if you are at that certain chemical potential in which you have a topological superconductor with a chiral Majorana mode, then as you change the chemical potential, you can go through a topological phase transition that gives rise to a gap closing, and eventually you are in a trivial state. So this topological phase transition between the trivial superconductor and topological superconductor, in principle, can be observed if you are capable of controlling the doping of your system. That, of course, is something that we can do in two-dimensional materials relatively often using just gates. So this is essentially everything that I wanted to tell you for today. So just as a reminder, as you know, we have at 1 the exercise session, and the idea is the same as in the other days. So you just have to download the session from GitHub or from the link in Team. And again, you have examples, and then you have questions that you can answer, and you can discuss with each other and also modify the code to see the results. So yeah, this is the last session of our school. So well, thank you so much for coming. It was a great pleasure to have you here, and see you in the afternoon in the exercise session.
Thank you, Jose. Before we go on for lunch, I would like to say a few words. Now, we got this idea